In example A, let's consider the function f of x equals x cubed plus 3x squared minus 4. We first want to determine the intervals of concavity. Remember when they ask for concavity, that's dealing with the second derivative. So let's find the first derivative first, and then take the derivative again for the second derivative to get 6x plus 6. And remember, if we set this equal to 0 and solve, will give us a possible inflection point at x equals -1. So once again, we're going to use our number line with -1 and plugging in this time to the second derivative because we're looking for concavity. Test point to the left, we can use, I don't know, -10 and maybe 0 to the right. Plugging it into the second derivative, give us a negative number, meaning it is concave down. And when we plug in 0 on the right-hand side, we get a positive number, which means it is concave up. For our concavity, we can say concave down from -infinity to -1. Remember that -10 was just a test point. Concave up from -1 to infinity. In part 2, they're asking us to find the intervals of increase and decrease and describe the rates. So remember, for intervals of increase and decrease, we need to find the first derivative, which we already found earlier, the 3x squared plus 6x, but we set that equal to 0 to find our critical values. After we factor and set each factor equal to 0, we get critical values of 0 and -2. So to find our intervals of increase and decrease, we'll use our number line method again. Plugging into our first derivative, we have a positive interval where it's increasing, our second interval where it's decreasing, and our third interval where it's increasing again. But remember, we need to figure out where it's increasing and decreasing, but also at what rate. So we are going to compare both number lines from part 1 and part 2. Using all of our critical values and hypercritical values from the first derivative and the second derivative, we're going to label the first derivative on top, and we're going to label the second derivative on the bottom. So the first derivative, notice here, is positive all the way up to -2. So everywhere from -infinity to -2. And then it's positive everywhere from 0 to the right. And it's negative everywhere between -2 and 0. Our second derivative is negative everywhere to the left of -1 and positive everywhere to the right of -1. Remember that the first derivative tells us if it's increasing or decreasing. The second derivative tells us if it's at a faster rate or a slower rate. So it is increasing at an increasing rate from 0 to infinity. How do we know that? F1 is increasing and F2 has the same sign. Where else does it have the same sign? Here and here. So the top tells us that it's decreasing. The fact that they're the same sign tells us that it's at an increasing rate. And that is between -2 and -1. Now here on the left, our first derivative is positive, so it's increasing. But our second derivative has a different sign. So it's increasing at a decreasing rate between negative infinity and negative 2. And our third interval there, our function is decreasing at a decreasing rate between negative 1 and 0. Example B, a company determines that it will sell Q of x equals negative 1/3 x cubed plus 60x squared minus 110x plus 5200, where it has a domain between 20 and 100 with the endpoints included, units of cola after spending X dollars in advertising in thousands of dollars. There's a couple of key pieces of information here that we want to focus on. Q, as in Q of X, is the units of cola. X is dollars in advertising, which is in thousands. Now notice the question is asking for us to determine the point of diminishing returns. That's where the rate of change of sales start to decrease. Rate of change of the sales, in other words, the inflection point. So we need to find the second derivative. The first derivative gives us a negative x squared plus 120x minus 100. Then our second derivative would be a negative 2x plus 120. So to find the inflection point, if there is one, we set it equal to 0. When we solve, we would get an x of 60. This is only a possible inflection point. In order for it to be an inflection point, remember the signs of the second derivative have to be different on both sides. So let's choose some test values, perhaps 40 and 70. Plug them into our second derivative and find the signs. So this tells us that it starts to become concave down, or that the rate of change starts to decrease after 60. So we can say point of diminishing returns occurs when we spend $60,000 in ads. And remember, it is an inflection point. So we can also find out not only the X value in ads, notice it's in thousands, but also we can find the number of units of cola. So we can plug in that 60 into our original function. So when we spend $60,000 in ads, we also sell 142,600 units of cola.